I thank you very much for the organizing committee. I'm very happy to be here. I'm doing this job in collaboration with another Roberto, who is my PhD student in Brazil, and also in collaboration with Javier, who provided the PSF data, Dante Miniti, and other VVV team members. And I would like to start with this image taken here in 2012, when we're here to discuss the next generation imaging surveys. And now, 11 years later, we're here to celebrate the success of the imaging survey. So I'm very happy to be in that image and to be back again here. So why head clump stars? Since our first analysis of the VVV data was very clear the presence of the head clump in our data, and head clumps can be used as distance indicators. They are very numerous, bright population one stars. So in the last decades, you see a lot of works using those stars as distance indicators, not only for a team, not only using VVV data, but using different data. And you decided to do this as well. So you made us advances in understanding the galactic structure using head clump stars, but always to select the line of signs. So you try it to go to the less extincted regions, sometimes looking for low extincted windows, and through these windows trying to map the head clump stars along all the bulge and disk. And the motivation for this work was the same. Here I'm showing a matched catalog between the VVV arbitrary data and Gaia. Gaia is optical data. So it's very clear that the density of stars decreases in the galactic center because of Gaia. Gaia is not able to see the other side of the galaxy. But this is interesting because you can see that even here, there are some regions that are most clear. These maps match reddening maps for the same region. I will show you later this. So the idea was, instead of use just a few line of sign, trying to do this analysis for a larger area, a continuous large area in the inner Milky Way. Okay, so here again is a density map combining now the DUFOT PSF data provided by Javier, which was discussed in the previous talk, now with Gaia DR3. So here is the VVVX area, below here and upper there, and this is the original VVV area, okay? And for this original VVV area, as Marina said, Francisco Surro made a very nice work in doing the DUFOT photometry and then providing a very fine reddening map for the outer bulge, okay? But we were not interested in the outer bulge because we're interested to see the other side of the galaxy. So you cannot go so far from +1 and -1 degree because here at the 15 kiloparsec from the sun, the high scale here is about half kiloparsec. So we're actually starting to lose the inner disk, okay? So you concentrate our work in this region between +1 and -1. And you try to map the red clump stars through all this region, but only for the cleaner regions, okay? So you look at the Francisco Surro maps, and we masked all the regions with EG, the excess of G minus key S color, larger than 2.2. And you have this, okay? This region in green and blue are the cleanest regions inside -1 and +1 and +10 and -10. So regarding all these regions and the regions of the more extincted regions was just masked. So it's still about 40% of this region here, and a lot of stars. Here is the total number of stars in beams of 1 degree. So the scale reason is a million of stars. Okay, so we still have millions of stars across all this region, even here. Okay, this is still thousands of stars. So you made use a recipe, transform the absolute the magnitudes and the colors of the head clumps in distance. Okay, using the absolute magnitude and a reddening vector. This for our work a few years ago when we analyzed a low extinction window very close to the galactic center. Okay, so with this recipe, we are able to transform the information of magnitude and color in distance. Okay, so here is the distribution of the selected red clump stars along the longitude and here in distance modulus. Okay, so here you can see there is this vertical fringe that coincides with our distribution of the stars. Okay, so this is not real, this is artifact created by your selection criteria. So here, where is the area is larger, there are more stars. Here, because the extinction is higher, there is a small number of stars, so these fringes are actually artifacts. But you can see there are actually at least two structures, this one here and that one farther. Okay, so we started the cooking. Okay, we started to clean up the data by slicing the data in longitude, and then for each beam doing histograms, trying to map the distribution, then subtracting the luminosity function. Okay, so after all these steps, you have now a smooth 2D surfaces, and we also interpolate the neighbors to create this. Okay, so this is a cleaner view of basic structures in the first plot. Here, we're not interested in the relative intensity of these structures. We're interested in trace, okay? We're interested in finding and tracing those structures. So you decided also to normalize this, okay? So for each line, each vertical line, we find the maximum, normalize for the maximum in order to highlight those structures, okay? Okay, so here we move from this to this and to this. And in this image, we fitted two main structures. One here that's very consistent along all the longitudes, and this other one that seems to connect here, and here has some kind of break that I will show you later. What is this? Okay, so at the beginning we interpreted this possible as the mapping of the spiral arm behind the bulge, and here the so-called inner bar that has been mapped by other works. Okay, so I will tell you more about these two regions. This one, what is this kind of connection, and his one seems to be a kind of break. Okay. So if you analyze this green circle here, from 7 to 9.5, you see that the head clamp has a double peak, as expected. And this region here, these peaks, should be this, okay? So we interpreted this possible as the Sagittarius arm behind the bulge. This other region is interesting because you can see here a peak. So here is a kind of plateau, it's more flat, and then it started to split in here, going toward us. Now, and that is another, maybe something in that direction. And we are interpreting this maybe as the beginning of the starting point of the X shape. Because if you started to see the galaxy to larger latitudes, There are several works showing that the head clump stars map an X shape, a box shape, different from the analysis of the Aralida, which are population too. So usually populations show this had this the X-shaped structure at larger latitudes. Okay, so here have also so this apparently break here is well mapped. It's just this peak that moves toward us, but still there's something in behind. And here in this blue circle, you can see from -6 to -3.5, so from here to here, that you have the single peak, okay, related to this. And this single peak again forms a kind of plateau here and becomes more intense in this direction than that direction. So this is still what are interpreted as the Sagittarius arm, and this front part is possible, the inner bar again. Maybe the beginning of the inner bar connecting with the spiral arm. Okay, so it's interesting to see the structures here, but it's also interesting to see the proper motions, because VVV has VIRAC, which is a proper motion catalog based on the VVV data, which for this region is about 13 years, as Martin said. But here I have some caveats, because this analysis was made with obsolete data. Okay, you use the CASU aperture data calibrated with DR2 data. This was made by Lee Smith, a few years ago. But as Martin said, there is a new version of this catalog using PSF data by Javier, much more accurate and calibrated with Gaia DR3. But it's important to see there are some differences in the proper motions, because sometimes when you see the double clamp, there's some works telling that the double clamp is not caused by two structures, but by the RGB bump. No, they say these are different populations, not the same population seen at different distance. So this is very promising. And now, we just last week was the VVV meet, I got the VIRAC 2 data, so I wanted to redo everything again to get better distribution of proper motion for our data. Okay, and this image is the same, to me it's okay, as I showed you previously, but now in physical coordinates. So I have distance, I have longitude, and I can transform this in xi. So the first structure is in here, and the structure in the back is there. And it's interesting because there was flat in this distribution of B mu versus B, and now it's an arc, okay? Very consistent, for instance, with some models. There is a issue here that our structures seem to be closer than us, than expected, for instance, for the values for the galactic center. But that seems to be caused by the reddening vector we choose, okay? Because you use a steeper value, and there is another recipe to this reddening vector, and it seems to be just a scale factor. If you come back to the scratch and do everything again, we're using a different reddening vector, we got larger distance, okay? And this distance can be now compared with simulations for our galaxies, or even for the view of our galaxy, and they're pretty consistent. So I'm very happy to see, for instance, the inclination, for instance, of these structures are consistent with the spiral arms, or the position of the first structure is in agreement with the galactic center. Okay, so I have to go fast now. So the idea now was extend the work. Okay, you made this for the inner region and look at very fine, and you redo everything again, but now using not only the region between -10 and +10, but between -20 and +20. You extended, we double the area. And here there's two plots in Belo, seems to be the same, but they're not the same, okay? The stars in the first plots are those stars that are stars of the VVV. Okay, all the VVV stars towards that region. And the bellow plot was the VVV data subtracted from Gaia. Okay, but Gaia data should be concentrated in the foreground disk. So if you take the VVV data and subtract all the Gaia data, which are in VVV, it should be a cleaner view of the second part of the galaxy. And this can be seen here. This would be the disk sequence that is almost missing in this part. Okay, so we lost 9 million of stars, but there's a foreground disk. And we made all the analysis again, now using the recipe that put the stars a bit farther. Okay, started from scratch again. And here are the results. This is the raw data, and this is exactly the same, okay, in the top and below. I'm just using like this combination, this color schema, and this is a kind of negative image, because sometimes it's better to see below than the other. Okay, so here in these green boxes, this is an artifact, because this is the maximum of the luminosity function distribution. So don't pay attention for that. This will appear. I could clean up this later by fitting the luminosity function. What you have to pay attention is that, oops, bellow. Okay, is that here, this region in green is shown here again, and here again, here is in blue, and all the structures are here. Okay, the Sagittarius arm is now seen extended. Maybe this is so-called a long bar. There's some work that call this region long bar. The inner bar is seen here again, and you see that maybe it's better to see here than here. There is another overdensity here that we interpret as the bar. Okay, so this is still still working on this. This is part of the PhD thesis of my student, this part. And the idea is to extend this, because this result is for just this one. Okay, the second part is this one. But VVV is all this area here. Okay, there's a lot of things to be done. And this is a first test I made trying to combine all the head clump stars in the innermost tiles, okay, using reddening-free indices. This is just a test I made to incentivize my student what I believe can be done. That is to map all the galactic disk using VVV data, okay? And Vista is still competitive in the future because, okay, you have now James Webb, but the field of view of James Webb is very small compared to VVV. So you want to go larger, okay, and map a larger area, you have to work with Vista and in the future with Hohmann Gracie telescope. And I think I'm done. Okay, thank you very much.